On January 14, 2005, a spacecraft named Huygens embarked on a historic mission. This was no ordinary spacecraft. It was designed to explore Titan, the largest moon of Saturn. Built and operated by the European Space Agency, ESA, Huygens was part of a larger mission led by NASA and ESA called Cassini. The journey began on October 15, 1997, with the launch of the Cassini spacecraft from Cape Canaveral Air Force Station in Florida. For 7 long years, Cassini traveled through the vast expanse of space, carrying with it the Huygens probe. On July 3, 2004, Cassini finally reached its destination, entering orbit around Saturn and beginning a new phase of its mission. With Saturn in sight, the stage was set for Huygens to undertake its own daring adventure, a descent onto Titan. Huygens was not just any spacecraft. It was built to withstand extreme temperatures ranging from 180 degrees C to plus 45 degrees C. To ensure its readiness for such harsh conditions, ESA conducted parachute drop tests from a balloon over northern Sweden in 1995. The pilot chute measured a precise 2.59 meters, just one of many meticulous details that went into preparing Huygens for its momentous mission. As the days counted down to Huygens' launch, the world watched with bated breath, awaiting what this little spacecraft would reveal about Saturn's mysterious moon. The Huygens probe launch on January 14, 2005, marked the beginning of a journey that would change our understanding of Titan forever. The launch of the Huygens probe on January 14, 2005, marked not just a singular event, but the culmination of an extraordinary mission collaboration. The probe itself was meticulously designed by ESA, engineered to withstand the extreme conditions of Titan's atmosphere. Loaded onto the Cassini spacecraft, Huygens carried 6 scientific instruments, each designed to measure specific aspects of Titan's environment during its descent. Among these was Haze, a device aimed at studying the magnetic field and electrical properties of Titan's atmosphere. The DISR camera system was another crucial component, capturing images that offered a first-hand glimpse into the mysterious world of Titan's surface. DWE, the Doppler wind experiment, measured wind speeds and directions, providing valuable data on Titan's atmospheric conditions. GCMS, the gas chromatograph mass spectrometer, analyzed the composition of Titan's atmosphere in remarkable detail. The ACP, or Aerobraking Control Program, was the onboard computer system that guided Huygens through its perilous descent. Finally, the SSP, or Surface Science Package, was designed to measure physical properties of Titan's surface after landing. It had been a long voyage, covering over 3.5 billion miles, launched aboard the Cassini orbiter 7 years prior. The probe traveled through space for nearly 2 hours before making contact with Titan's atmosphere. To slow down during its descent, Huygens used a parachute system, 3 different parachutes deployed in sequence. The first, known as the pilot chute for transonic stability, was released at an altitude of 40 kilometers. This initial parachute stabilized the probe as it entered Titan's transonic region, where airflow transitions from subsonic to supersonic speeds. As Huygens continued its descent, the main parachute was deployed, further reducing the probe's speed. The entire descent process lasted approximately 2 hours and 30 minutes. Finally, at 10:30 a.m. Central European Time on January 14, Huygens successfully landed on Titan's surface. First among these was Haze, the Huygens Atmospheric Structure Instrument. Designed to measure atmospheric structure, HASE started its work immediately upon entering Titan's atmosphere. It provided valuable data on the temperature, pressure, and air density of Titan's atmosphere, helping scientists understand its complex layers. Next was DWE, the Doppler wind experiment. This instrument was tasked with gathering crucial wind speed and direction data. As Huygens descended, DWE sent radio signals that bounced off the probe's surface to measure the movement of air around it. DISR, the Descent Imager Spectral Radiometer, was responsible for capturing the first ever images of Titan's surface. As Huygens plunged through Titan's atmosphere, the ISR snapped over 700 images, revealing a landscape unlike any on Earth. It sampled and studied the gases present, including methane and other hydrocarbons that are crucial to Titan's unique atmosphere. ACP, the aerosol collector and pyrolyser, had a very specific job, collecting samples of aerosols present in Titan's atmosphere. These aerosol particles are tiny solid or liquid droplets suspended in the air, and studying them can reveal much about Titan's atmospheric processes. Lastly, SSP, the surface science package, included accelerometers to study surface properties and a microphone that captured the faint sounds of Titan's wind. As Huygens touched down on Titan's surface at 9004 UTC, these instruments worked together to provide a wealth of data that would revolutionize our understanding of this distant moon. Titan is no ordinary moon. With an average surface temperature of 179 degrees C, it's one of the coldest places in our solar system. The landing site in the Xanadu region was chosen for its Earth-like geography, where liquid methane flows like water on our planet. Upon landing, Huygens deployed its instruments to gather data about the surface and atmosphere of this distant world. This historic event was a significant milestone in our quest to understand the outer reaches of our solar system. The first images sent back by Huygens revealed a landscape unlike anything we've ever seen. Smooth, dark plains stretched out in every direction, with rounded hills and mountains scattered across the horizon. This landing on Titan marked a revolutionary moment for space exploration. It was the first time we had touched down on an outer solar system body, opening up new avenues of discovery and understanding. As Huygens transmitted its findings back to Earth, it highlighted the immense scientific contributions that this mission would bring. But the story of Titan was just beginning. The Surface Science Package, SSP, onboard Huygens studied the physical properties of Titan's surface. This instrument was crucial in understanding the solid ground beneath all that methane rain and wind. Imagine standing on a shoreline of an icy lake with your boots sinking slightly into the slushy surface. That's what Huygens experienced as it touched down on Titan, except instead of water, it was liquid methane. The scientific contributions from the Huygens mission are monumental. They have paved the way for future missions like NASA's Dragonfly, which aims to explore Titan in even greater detail. As we continue to unravel the mysteries of this icy moon, each discovery brings us one step closer to understanding whether life beyond Earth might be possible after all. For now, Titan remains a puzzling yet fascinating world in our solar neighborhood. Its organic, rich atmosphere and icy landscapes offer both challenges and opportunities for future exploration. Each finding from Huygens is like another piece of the puzzle, helping us slowly put together the picture of this enigmatic moon. Huygens' achievements on Titan have profound future implications. The probe's success was a crucial step in exploring the outer solar system, setting the stage for more ambitious missions. Each discovery from Huygens is another piece of the puzzle, helping us slowly unravel the mysteries of this enigmatic moon. Its data on Titan's atmosphere, temperature, and surface composition are key to planning future missions. The mission also showed that Titan could support a lander, which is essential for understanding the moon's geological processes and environmental conditions. This opens doors for more sophisticated landers in the future. Future studies can now build upon Huygens' legacy, venturing deeper into Titan's mysteries. The probe's hardy design, which protected its delicate interior from extreme temperatures, has provided a blueprint for future missions. As we delve further into the cosmos, the lessons learned from Huygens will guide us in exploring other moons and celestial bodies in the outer solar system. Its achievements echo far beyond Titan, inspiring a new era of space exploration. The Huygens mission not only expanded our knowledge, but also demonstrated the potential for future robotic explorations in harsh environments. Its success story is a beacon for what can be achieved with innovative engineering and perseverance. In conclusion, the historic Huygens probe landing on Titan's surface marked a turning point in our understanding of the outer solar system. Its enduring legacy will continue to shape future missions and discoveries, paving the way for even more extraordinary revelations. It's September 15, 2017. The Cassini spacecraft, after nearly 2 decades of groundbreaking exploration, is on its final approach to Saturn. This isn't just another maneuver, it's the calculated end of an era. The entry assembly module, a crucial component of Huygens, carried equipment to control the probe after separation from Cassini and provided thermal protection during entry. The atmospheric pressure at Titan's surface is approximately 1.5 bars, denser than Earth's atmosphere at sea level. This dense environment was ideal for Huygens' data collection. On December 25, 2004, Huygens separated from Cassini and began its historic descent towards Titan's surface, a journey that would take over 2 hours. During its mission, Cassini discovered significant findings, such as the salty ocean spray from Enceladus's geysers, and provided invaluable data about Titan's methane lakes. The Cassini spacecraft's final moments were carefully choreographed to ensure it didn't contaminate Saturn's moons, particularly Enceladus and Titan. The mission's conclusion wasn't just a technical feat, it was also a testament to the power of international cooperation in space exploration. Cassini's entry into Saturn's atmosphere after nearly 20 years of service symbolized the end of an era and paved the way for future missions to build upon its legacy. The historic landing of Huygens on Titan's surface, combined with Cassini's extensive discoveries, has left an indelible mark on our understanding of the outer solar system. From unraveling Titan's mysteries to revealing Enceladus's icy plumes, this mission has reshaped our perception of the cosmos. As we look back on Cassini and Huygens, we are reminded that every ending is a new beginning in the vast expanse of space exploration. As the historic Huygens probe landed on Titan, it revealed a world shrouded in mystery. Yet for all its discoveries, unresolved questions about this enigmatic moon remain. Despite Huygens' groundbreaking mission, the geological features of Titan continue to puzzle scientists. How were these structures formed, and what do they reveal about the moon's past? And what of the moon's atmospheric phenomena? The winds that howl across its surface, the storms that rage in its skies, are they driven by forces we can barely comprehend? The Huygens probe provided invaluable data during its brief stay on Titan, but it also raised more questions than it answered. It's a reminder that every discovery is just the beginning of another mystery. As we gaze at this distant world, we can't help but feel a kinship with those who first dared to dream of exploring other planets. They too must have looked out into the cosmos and wondered, what secrets lie hidden beyond our reach? And so, Titan remains a puzzle waiting to be solved. A tantalizing enigma that draws us in with its promise of discovery and the thrill of the unknown. As we continue our journey through space, let us embrace these mysteries, for they are not barriers but beacons, guiding us towards the next great adventure in our endless quest to understand the universe. And perhaps one day, as we stand on the shores of an alien sea or gaze up at a sky filled with strange and wondrous sights, we will find that Titan's secrets were just the beginning. Huygens' legacy includes unraveling the mysteries of Titan through its groundbreaking mission and paving the way for future explorations. That means all the dinosaurs, the Ice Age, and even the first signs of life would have come and gone before we made our debut. This is what scientists often refer to as the Milky Way Analogy. Imagine a calendar year divided into 12 months, each representing around 2.7 million years of Earth's history. Now, break that down even further. Every single day of the month stands for approximately 200,000 years. This helps put into perspective how young our species is in the grand scheme of things. When we look up at the night sky, gazing at the stars, we're witnessing light that has been traveling for billions of years. It's a humbling reminder of how tiny our place is in the cosmos and just how short our time as a species has been so far. The Cassini-Huygens mission, which included the historic landing of the Huygens probe on Titan in 2005, is a prime example of this vast timescale. From its launch in 1997 until its dramatic end in 2017, the entire journey took over 2 decades, a blink of an eye in cosmic terms. This mission was a testament to human ingenuity and our ceaseless quest to understand the universe around us, no matter how brief our presence may be. Titan's methane lakes are vast and expansive, reminiscent of our own Earth's oceans, but composed entirely of liquid methane. These lakes form at the poles, where temperatures are extreme enough to freeze methane, creating a landscape that is both familiar and alien at the same time. Imagine standing on the shore of one of these methane seas. The surface beneath your feet is cold and hard, unlike the sandy beaches we are familiar with. Each lake is a unique ecosystem within itself, teeming with life that has adapted to thrive in this methane-rich environment. With its hazy orange skies and vast lakes of liquid methane, Titan is a world unlike any other in our solar system. To understand the chemistry that makes Titan so unique, we need to explore its atmospheric composition. The primary component of Titan's atmosphere is nitrogen, making up about 98% of the air. This is similar to Earth's atmosphere, which is about 78% nitrogen. What sets Titan apart, however, is the presence of methane. Methane makes up about 1.4% of Titan's atmosphere, and it's this gas that gives Titan its distinctive orange haze. Other gases like argon and hydrogen are also present, but in much smaller quantities. The GCMS instrument aboard the Huygens probe analyzed this complex mixture during its descent. This detailed chemical data was crucial for understanding the processes that shaped Titan's atmosphere. By unraveling these mysteries, we can begin to piece together the story of how Titan came to be so different from other worlds in our solar system. As we delve deeper into this journey of discovery, the wonders and peculiarities of Titan's environment continue to unfold. These peculiar formations piqued scientists' curiosity as they seemed out of place on a moon primarily composed of ice and rock. The images sent back by Huygens showed these rocky outcrops scattered across the surface, challenging initial assumptions about Titan's geological makeup. The presence of these sand dunes suggests a dynamic atmospheric process at work on Titan. As methane gas flows over the surface, it can pick up and transport tiny particles, leading to the formation of these unique hydrocarbon-rich dunes. As Huygens continued its descent and eventually landed on Titan's surface, it also captured glimpses of icy peaks that pierced the horizon. These mountains are thought to be composed mainly of water ice, making them a stark contrast to the rocky outcrops and sand dunes. The varied terrains spotted by Huygens, rocky structures, sand dunes, and icy mountains, paint a picture of a world that is both familiar and alien. By examining these features, scientists gain valuable insights into the intricate processes shaping Titan's surface. Through this historic landing, Huygens offered a deeper understanding of the varied landscapes that make up Titan's surface, further deepening our knowledge of one of the most enigmatic moons in our solar system. The parachute that helped slow Huygens' descent was crucial in allowing the instruments to gather precise data about these wind conditions. It revealed a dynamic weather system where strong winds can shape and reshape the landscapes over time. The data collected by Huygens offers a glimpse into the vast and varied landscapes of Titan, shaped over eons by the forces of wind, precipitation, and seasonal changes. It's a testament to the resilience and adaptability of this unique celestial body that continues to captivate scientists and astronomers alike. As we continue to explore Titan, each new discovery deepens our understanding of this extraordinary moon, shedding light on the mysteries of its surface and the dynamic forces that sculpt it over time. Huygens used a combination of primary and secondary batteries to ensure it could operate effectively throughout its mission. The primary battery provided the main power source during the probe's descent through Titan's atmosphere. While still attached to the Cassini orbiter, Huygens relied on solar arrays for supplemental power. These arrays converted sunlight into electrical energy, helping to maintain the probe's battery charge during its journey. The role of these solar arrays was particularly crucial as Huygens prepared for its separation from Cassini and the subsequent descent to Titan's surface. The successful operation of these power systems was a testament to the engineering prowess behind the Cassini-Huygens mission. As we continue to explore Titan and its mysteries, the technical achievements of this historic event serve as a beacon for future expeditions. As we delve deeper into these mysteries, the power systems that supported Huygens on its journey stand as a testament to human ingenuity and our relentless pursuit of knowledge. The technical challenges overcome during the historic Huygens landing illuminate not only the vastness of space, but also the incredible lengths we go to in our quest for understanding. Data transmission was the lifeline that connected Huygens to Earth. The Cassini orbiter played a critical role in this intricate process. First, the probe had to capture and compress the data. The Cassini orbiter then received this compressed information through a dedicated antenna. The data traveled at the speed of light across the vast expanse of space to reach Cassini's antenna. Despite this incredible speed, it still took over an hour for the signal to reach Cassini. Once received by Cassini, the data was decoded and relayed back to Earth through the Deep Space Network. This complex process highlighted the incredible lengths we go to in our quest for understanding. Each step was crucial in ensuring that every piece of data from Titan's surface reached us intact. And for a brief but remarkable window of time, we were able to see and learn from this alien world through the historic Huygens probe landing. When Huygens entered Titan's atmosphere, it faced temperatures as low as 180 degrees, 2292 degrees Fahrenheit. The probe had to survive these extreme conditions without freezing solid or overheating from the sun's rays. The descent module itself was encased in a unique heat shield to withstand the intense heat generated during atmospheric entry. This shield played a dual role, acting both as thermal protection and ensuring stable descent. During its descent, Huygens encountered several challenges related to heat management. It had to deal with the intense heat from friction as it plunged through Titan's atmosphere at speeds up to Mach 2.4. The final parachute, measuring 2.59 meters in diameter, gently brought the probe to a landing on Titan's surface. This final stage was crucial for ensuring Huygens didn't overheat from the residual atmospheric friction. Engineering such a probe to withstand and function in extreme environments like Titan is no small feat. It demonstrates the remarkable ingenuity required to explore distant worlds in our solar system. Image processing involves various techniques to improve the quality and clarity of images. Methods like enhancing contrast, adjusting brightness, and using filters can reveal details that might otherwise go unnoticed. By applying these methods to the images sent by Huygens, scientists have been able to see Titan's surface in astonishing detail. They can make out features like riverbeds and rock formations that are reminiscent of Earth's landscapes, but shaped by the unique conditions on Titan. One key finding from image analysis is the presence of what appears to be sediment deposits, similar to those found in river deltas or lake beds on Earth. This suggests that liquid hydrocarbons may flow across Titan's surface, shaping its geology over time. The challenges in processing this data are significant. The images have to be calibrated and corrected for the effects of Titan's thick atmosphere and low temperatures. Scientists must also account for the long distance the signals traveled before reaching Earth. Despite these obstacles, the image processing of Huygens' data has been instrumental in advancing our understanding of Titan. It provides a window into a world unlike any other we have explored, offering insights that could help in planning future missions to this enigmatic moon. The raw data from Huygens is transformed into meaningful scientific insights through meticulous work and advanced techniques. This process showcases the ingenuity required not just to send probes to distant worlds, but also to make sense of what they find. The journey of the Huygens probe has not only expanded our cosmic horizons, but also underscored the importance of careful, precise image processing in uncovering the mysteries of distant worlds. With each new discovery, we inch closer to understanding our solar system's most enigmatic bodies, and perhaps, one day, finding answers to the fundamental questions that drive our exploration. But Titan's organic chemistry doesn't stop there. More complex hydrocarbons were also found. These organic compounds are relevant to astrobiology, the study of the origin and distribution of life. Although there is no definitive evidence yet, the presence of these compounds raises intriguing questions about the potential for life under certain conditions. As we continue to explore our solar system's most enigmatic bodies, each new discovery brings us a step closer to unraveling their mysteries. Communicating over vast distances was another significant hurdle. Once Huygens separated from Cassini, it had to function autonomously for the entire descent through Titan's dense atmosphere. The main parachute further decelerated the probe, ensuring that its landing was as soft as possible on Titan's surface. The final stage of descent included the use of a drag brake to ensure controlled and safe touchdown. The technical ingenuity behind the Huygens mission makes its achievements all the more impressive. From designing a probe to withstand extreme temperatures to ensuring autonomous operation and precise communication, every aspect of this mission showcases humanity's relentless pursuit of understanding our cosmic neighbors. The engineering feats behind the Huygens probe are a testament to human innovation and our unyielding curiosity about the cosmos. Beyond the intricate engineering that made Huygens' journey possible lies another layer of wonder: the atmospheric dynamics of Titan itself. Titan's atmosphere is a thick haze of nitrogen and methane, where wind patterns and storms carve the landscape in ways that are both familiar and entirely alien. Imagine winds strong enough to sculpt mountains out of liquid methane. That's the reality on Titan. Huygens' measurements revealed wind speeds reaching up to 60 kilometers per hour during its descent through Titan's atmosphere. This might sound tame compared to Earth's hurricanes, but on a world where wind can shape mountains of liquid hydrocarbons, these winds are sculptors of geological scale. The data sent back by Huygens provides a glimpse into the complex interplay between Titan's atmosphere and its surface features. Titan storms are not like the ones we experience on Earth. They're vast, slow-moving systems that can darken the sky for weeks. Huygens helps scientists understand how these storms deposit methane rain on the surface, which then evaporates and cycles back into the atmosphere. This continuous cycle shapes Titan's unique geological features over millennia. As the probe descended, it sent back images of a world carved by relentless winds and shaped by the ebb and flow of methane rain. These images provide a comprehensive look at how Titan's atmosphere sculpts its surface, offering us an unprecedented glimpse into the workings of this alien world. This moon offers a unique opportunity to study complex organic chemistry in an environment similar to that of certain exoplanets, planets outside our solar system. These findings broaden the context of Huygens' mission by showing its relevance to the broader field of exoplanet research. Though we cannot yet visit these distant worlds, Titan serves as a real-world laboratory for understanding their complex chemistry and potential for life. By unraveling the mysteries of this alien world through the lens of exoplanet analogies, we gain a deeper appreciation for the diversity and complexity of our cosmic neighborhood. As we continue to explore the outer reaches of our solar system, each discovery on Titan brings us one step closer to understanding the infinite possibilities in the universe. Imagine standing on Titan's shoreline. The liquid before you isn't water but methane, a simple hydrocarbon that on Earth is often found in natural gas. The wind ruffles the surface, creating ripples that shimmer under the dim light of Saturn. These bodies of liquid methane and ethane are scattered across Titan's surface, some as large as Earth's Great Lakes. Unlike water on Earth, these hydrocarbons can evaporate into Titan's atmosphere, condense back into rain, and then collect in low-lying areas to form lakes and seas. Titan's lakes and seas are not merely a curiosity. They hold clues to the Moon's geological history and potential habitability. The formation of these hydrocarbon bodies hints at a complex interplay between Titan's climate, atmospheric chemistry, and surface topography. While Earth's oceans are critical for life as we know it, the existence of liquid methane on Titan presents a unique challenge. These hydrocarbons could host life forms adapted to this harsh environment, but they also pose significant obstacles to traditional biological processes. The next time you look up at the night sky and see Saturn's distant glow, remember Titan's hydrocarbon lakes and seas. They are not just a distant mirage, but a real and fascinating part of our cosmic neighborhood waiting to be explored. As we delve deeper into the intricacies of Titan, each discovery not only enriches our understanding of this moon, but also broadens our horizons about the infinite possibilities in the universe. As Huygens descends through this Tholin atmosphere, its observations are influenced by these particles. The probe's instruments must work through this thick haze to gather data about Titan's surface and subsurface. The presence of tholins not only affects visibility, but also impacts the way sunlight is scattered in Titan's atmosphere, creating a unique optical phenomenon known as Rayleigh scattering. This scattering gives Titan's sky its distinctive orange hue. Understanding this Tholin atmosphere is key to deciphering the intricate dynamics of Titan's environment. It provides valuable insights into not only the Moon's current state, but also its past and future evolution. The Huygens mission paves the way for future explorations like NASA's Dragonfly mission. By enhancing our understanding of Titan's Tholin atmosphere, we inch closer to unveiling the mysteries of this fascinating world and our cosmic backyard. The intricacies of Titan's Tholin atmosphere remind us that there is still so much to learn about the cosmos, and every new piece of information brings us one step closer to unlocking its secrets. In this vast universe, each planet and moon holds its own unique story. And with missions like Huygens, we are writing chapters in the epic tale of cosmic discovery, one fascinating revelation at a time. Winds on Titan were found to be relatively calm, typically blowing at a gentle 1 meter per second. However, sudden gusts reaching up to 3 meters per second occasionally swept through the probe's path. These wind speeds were crucial in understanding Titan's weather patterns and atmospheric dynamics. Titan's atmosphere is denser than Earth's, with densities ranging from about 5 to 15 kilograms per cubic meter. This density made the probe's descent more challenging, requiring careful aerodynamic control to slow down and stabilize. Temperature readings from the Haze also provided significant insights during the descent. This data highlighted how Titan's thick atmosphere traps heat, creating a warmer surface environment. Combining these readings with wind speed measurements allowed scientists to paint a detailed picture of Titan's complex atmospheric conditions. This unprecedented data analysis continues to deepen our understanding of this intriguing world, providing invaluable insights for future missions. The probe discovered that the surface rocks and soil are primarily composed of water ice, with traces of organic materials. This comprehensive look at Titan's surface composition offers intriguing implications for the potential existence of life under certain conditions. The probe's heat shield absorbs most of this heat, but the intense friction and compression still pose significant challenges. To combat this, Huygens uses a sequence of 3 parachutes to gradually slow its descent through Titan's dense atmosphere. This initial parachute stabilizes the probe's descent as it plummets through Titan's atmosphere at transonic speeds. Once conditions are stable enough, Huygens deploys its main parachute, which spans a massive 83 meters in diameter. The main parachute dramatically slows the probe's descent, bringing it from supersonic speeds to a more manageable subsonic pace. Finally, as the surface of Titan looms closer, Huygens deploys its third and smallest parachute, measuring 2 meters in diameter. These insights offer intriguing implications for the potential existence of life under certain conditions on this distant world. Using a parachute to slow its descent, the Huygens probe carried 6 scientific instruments designed to study the physical properties of Titan's surface. One of these instruments was the Surface Science Package, SSP, which provided invaluable data on Titan's surface texture. From the moment Huygens began its descent, every sound wave echoed through Titan's dense atmosphere was a clue waiting to be deciphered. As Huygens plummeted through Titan's thick atmosphere, it captured minute fluctuations in air density. These measurements provided critical insights into the complex wind systems that sculpt the Moon's surface. But what makes this data particularly fascinating is its potential to reveal hidden structures beneath Titan's surface. Sound waves, when they encounter abrupt changes in density, like those over subsurface voids or tunnels, undergo reflections and distortions. By carefully analyzing these acoustic anomalies, scientists can infer the presence of intricate underground structures. This is more than just a measurement. It's like listening to Titan whisper its secrets. Imagine standing on Earth and hearing the distant rumble of an underground river or the muffled echoes within a cavernous tunnel. Now think of Titan's acoustic whispers as providing similar insights into its geological makeup. With each new piece of data, the mystery of Titan unravels further, revealing a world far more complex and wondrous than we initially imagined. The acoustic measurements taken by Huygens during its descent and time on the surface have opened up new avenues of research into Titan's intricate environmental dynamics. The mission's technological advancements, such as the use of parachutes and advanced communication systems, were instrumental in navigating Titan's dense atmosphere. These innovations have paved the way for future spacecraft designs to tackle similarly challenging environments. The scientific goals inspired by Huygens extend beyond the initial mission's objectives. Its success in measuring atmospheric composition and temperature variations has set a benchmark for future probes aiming to study complex environments elsewhere in the outer solar system. These findings are instrumental in planning future missions that seek to understand the dynamics of other distant worlds. The legacy of Huygens is an enduring one, shaping the ambitions and design principles of space exploration today. Its pioneering achievements ensure that more ambitious missions will continue to build upon its foundation, reaching ever further into the cosmos in search of new discoveries. The lessons learned from Huygens are not just about technological prowess, but also about the human ingenuity and curiosity that drive us to explore the unknown. To understand Titan's geological history, we must delve into how its icy surface formed and evolved over time. Scientists believe that Titan began as a ball of ice and rock in the outer solar system. Over eons, this primordial body was shaped by impacts from space debris. These collisions caused the icy surface to melt and refreeze, a process that repeated countless times as Titan grew. As the surface froze and thawed, it created a complex network of fractures and ridges similar to what we see on Earth's icy surfaces. The key difference is that Titan's ice is methane-rich, giving its landscape a unique character. Methane on Titan acts like water does on Earth. It flows in liquid form and evaporates into the atmosphere, only to fall back as rain. This methane cycle shapes Titan's landscape, creating riverbeds, lakes, and even a vast ocean of liquid methane in the Moon's North Pole. The Huygens probe, as it descended to Titan's surface, captured images and data that corroborate these theories. It sent back pictures of a world shaped by methane rivers and lakes, providing tangible evidence of Titan's geological history. This wealth of information allows scientists to piece together a clearer picture of how Titan has evolved over time. By studying the past and present of this enigmatic world, we deepen our understanding of planetary formation and evolution. Titan's geological history is a testament to the dynamic processes that shape our universe, seen vividly through the lens of Huygens' discoveries. Atmospheric lightning is a phenomenon where electrical charges build up within clouds and are then discharged in powerful flashes of light. The discovery of atmospheric lightning on Titan is significant because it offers insights into the complex methane cycle that shapes this alien world. Like Earth's water cycle, Titan's methane cycle involves the evaporation of methane from lakes and seas, its condensation into clouds, and subsequent rainfall. The electrical discharges of atmospheric lightning may play a crucial role in the distribution and deposition of methane particles within Titan's atmosphere. Comparing this to Earth's lightning, it becomes evident that the presence of atmospheric electrical activity on Titan could provide valuable clues about the dynamic processes governing its unique environment. This newfound knowledge, uncovered by Huygens' historic landing on Titan, highlights the complex interplay between electrical phenomena and atmospheric chemistry in environments far different from our own. As the probe continued to transmit data, it painted a vivid picture of an alien world teeming with mysteries and dynamics that resonate deeply with the scientific quest to understand our cosmic neighborhood. The Huygens probe continued its descent, piercing deeper into Titan's atmosphere. This alien world, bathed in a golden haze of methane, was slowly revealing its secrets. As the craft plunged further, it unveiled an intricate layer within Titan's skies, an ionosphere. The ionosphere is a region in the upper atmosphere where neutral particles are ionized by solar radiation or other sources of energy. Titan's ionosphere is especially noteworthy because it interacts directly with Saturn's powerful magnetosphere. The interaction between Titan's ionosphere and Saturn's magnetosphere creates a dynamic interplay of charged particles and magnetic forces. As Huygens descended, it captured data that illustrated this complex dance between the two celestial bodies. The presence of an ionosphere on Titan suggests that atmospheric escape processes are at play. These processes involve the gradual loss of gases from Titan's atmosphere into space due to the influence of Saturn's magnetic field. The ionosphere serves as a bridge between Titan's atmosphere and the magnetospheric environment of Saturn. Understanding this interaction is crucial for deciphering Titan's atmospheric dynamics and its role within the broader Saturnian system. The discoveries made by Huygens during its descent provided invaluable insights into these intricate processes. As the probe sent back its final transmissions from Titan's surface, scientists were left with a wealth of data that illuminated the complexities of this alien world. This new understanding has opened up avenues for future exploration, aiming to unravel more of Titan's secrets. The mysteries of the Saturnian system deepen as we delve further into the enigmatic world of Titan. Another critical aspect was power management. The probe had to operate in environments where sunlight was barely perceptible, making solar energy impractical. To address this, Huygens used a set of advanced batteries that provided stable power throughout its descent and landing sequence. As we continue to push the boundaries of space exploration, the ingenuity behind Huygens serves as a testament to what humanity can achieve with cutting-edge technology and unwavering determination. These engineering achievements are not just technical marvels. They represent our collective ambition to unlock the secrets of the universe, one discovery at a time. Theories suggest that subsurface oceans on Titan could be composed of a mixture of liquid water and ammonia. This intriguing hypothesis is supported by Cassini's observations of methane rain and rivers, which hint at the presence of complex hydrological cycles beneath Titan's frozen crust. Cassini's radar measurements also indicated a smooth surface beneath Titan's icy shell, suggesting that the moon might be hiding vast bodies of liquid. These findings have significant implications for astrobiology, as they open up the possibility that conditions favorable to life could exist within Titan's interior. Despite these tantalizing clues, definitive proof of liquid water oceans on Titan remains elusive. Scientists continue to investigate the enigmatic moon, striving to unravel its deepest secrets through a combination of remote sensing and future missions like NASA's Dragonfly. The potential existence of subsurface oceans on Titan carries profound astrobiological implications, suggesting that the conditions necessary for life as we know it could be present in unexpected places across the cosmos. As our understanding deepens, so does our wonder at the universe's complex and often counterintuitive nature. The mysteries of Titan's subsurface oceans remain as vast and enigmatic as the cosmos itself, waiting patiently for our continued exploration and understanding. Each new discovery brings us one step closer to unraveling the secrets of this extraordinary world hidden beneath a frozen exterior. In this quest for knowledge, the historic landing of the Huygens probe serves as both a milestone and a beacon, a testament to our collective ambition to unlock the universe's deepest secrets, one discovery at a time. And so we delve deeper into the enigmatic world of Titan, guided by the pioneering spirit of Huygens and the endless curiosity that drives us to explore the cosmos. The tale of Titan's subsurface oceans is far from over. Rather, it is just beginning to unfold. Tidal forces exert a powerful pull on Titan, shaping its surface and atmosphere in remarkable ways. This close proximity means that Titan is heavily influenced by Saturn's gravitational pull. The tidal forces generated by this proximity create a continuous tug on Titan's surface and atmosphere. These forces cause the moon to be slightly elongated along its axis that points towards Saturn. This tidal stretching also affects the surface of Titan, inducing tectonic activity. The resulting stresses on Titan's crust can lead to the formation of geological features such as fault lines and ridges. In addition to shaping its surface, tidal forces influence Titan's atmosphere in intriguing ways. The gravitational pull of Saturn creates a slight atmospheric bulge on the side of Titan facing its host planet. This bulging effect can lead to wind patterns that circulate around Titan's atmosphere. The interaction of these forces highlights the dynamic relationship between Titan and its host planet, Saturn. Through the historic Huygens probe landing, we gained insights into how these tidal influences shape this enigmatic moon's environment. These organic aerosols play a pivotal role in Titan's atmospheric dynamics. They can influence the planet's energy balance by absorbing and scattering sunlight, creating a unique climate that is distinct from any other known environment. Understanding these aerosols is not only fascinating but also vital for future missions, aiming to explore the possibility of life beyond Earth. Through its groundbreaking analysis, Huygens has provided deeper insights into Titan's atmospheric aerosols, shedding light on the complex chemistry that shapes this distant world. The seasonal cycles on Titan are profoundly different from those on Earth, shaped by its unique composition of nitrogen and methane. This dynamic interplay between these gases creates a climate system that is both familiar and alien at the same time. Geological evidence suggests that Titan has experienced significant past climate shifts, with periods of increased surface temperatures and changing atmospheric compositions. These shifts are thought to be influenced by the solar cycle and the gradual cooling of Saturn's interior, providing a glimpse into the intricate balance of forces at play. Predictions for future conditions on Titan are subject to considerable uncertainty, but hold immense promise. Scientists believe that understanding the long-term climate changes on Titan could help us unravel the broader mysteries of planetary climatology, including potential clues about life beyond Earth. Titan's atmosphere is dense and composed mainly of nitrogen, with traces of methane. This creates a unique aerodynamic environment that the probe had to navigate. Wind conditions on Titan are generally calm and steady, but the probe still faced significant aerodynamic forces as it sliced through the atmosphere. The data collected by Huygens has provided invaluable insights into Titan's complex climate system, helping scientists better understand the dynamics of our own planet's atmosphere. As it reached Titan's surface, Huygens' descent module separated from the parachute and began collecting data about the physical properties of the Moon. By unraveling the mysteries of Titan through the historic Huygens probe landing, scientists continue to shed light on the broader questions about life beyond Earth. This discovery was particularly exciting because it suggests that the building blocks of life as we know it might be present on Titan's surface. Huygens also detected a complex mix of gases in Titan's atmosphere, including methane and ethane, which rained down onto the surface, contributing to its unique landscape. Understanding Titan's surface material composition is not just fascinating, it brings us one step closer to answering the broader questions about life beyond Earth. As the Huygens probe descended through Titan's dense atmosphere, it carried a special instrument designed to capture something entirely new: acoustic signals. DISAR's unique design allowed it to record the subtle acoustic vibrations caused by wind and surface interactions, providing scientists with a new way to understand Titan's environment. The probe recorded wind speeds of up to 35 meters per second, nearly 4 times faster than the strongest hurricane winds on Earth. As Huygens neared the surface, DISR also picked up mysterious subsurface sounds that scientists are still working to decode. Each new piece of information brings us closer to unlocking the mysteries of this distant world and its potential for life. As Huygens descended through Titan's thick atmosphere, one of the most striking discoveries was its unique atmospheric haze. This orange-brown haze layer envelops Titan, creating a dense shroud that obscures the Moon's surface from view. These tiny particles scatter light in ways that make Titan appear hazy and orange-brown from space. Despite the dense haze, Huygens managed to send back over 700 images during its descent, offering a glimpse into this mysterious world. These insights provide deeper understanding of Titan's atmospheric conditions and the challenges faced by future missions exploring its surface. Measuring wind speeds at different altitudes provided invaluable data on the vertical structure of Titan's atmosphere. This revealed that winds near the surface were generally lighter than those at higher altitudes. In fact, wind speeds close to Titan's surface were found to be significantly lower compared to measurements taken during the initial phases of descent. The Huygens probe also recorded temperatures that fluctuated throughout its journey, providing insights into Titan's thermal structure and its impact on atmospheric dynamics. These temperature variations, along with pressure readings obtained by Haze, offered clues about the interactions between different layers of Titan's atmosphere. Pressure data from Haze revealed a gradual increase as the probe approached the surface, suggesting that the dense lower layers of Titan's atmosphere are subject to more intense compression. These observations not only deepened our understanding of Titan's atmospheric conditions, but also highlighted the intricate climate dynamics at play on this distant moon. By unraveling these meteorological mysteries through in-situ measurements, the Huygens probe has laid a foundation for future missions aiming to explore Titan's surface and its complex weather systems. This journey into the heart of Titan's atmosphere, though brief, has opened new avenues for comprehending the celestial body's unique environment. Despite the exciting implications, it's essential to approach these discoveries with caution. Speculation about extraterrestrial life must be clearly framed within what is known and observed. As we delve deeper into Titan's secrets, the journey of Huygens becomes even more remarkable. It's not just about unraveling the mysteries of a distant world, but also understanding the possibilities that lie within the vast cosmos. The story of Titan, like so many celestial bodies, is one of endless fascination and discovery. As we continue to explore the cosmos, each new piece of knowledge adds layers to our understanding of life and its origins in the vast expanse of space. As the Huygens probe hurtled towards Titan, it faced a daunting challenge: atmospheric entry heating. At nearly 22 kilometers per second, friction with the dense atmosphere would generate immense heat. The probe was equipped with a sophisticated heat shield designed to withstand temperatures up to 1650 DC. This shield, crucial for protecting Huygens' sensitive scientific instruments, was the first line of defense against the searing heat. Titan's atmosphere is 4 times denser than Earth's, creating intense aerodynamic forces that threaten to rip Huygens apart. To mitigate these forces, the probe was designed with a blunt, conical shape to reduce drag. The heat shield also played a vital role in managing these aerodynamic forces. Its curved surface helped deflect some of the airflow, further reducing the stress on the probe's structure. Inside the probe, an intricate system monitored and managed these conditions in real time. Sensors continuously tracked temperature, pressure, and other vital signs to ensure that Huygens stayed within operational limits. Despite the intense heat, the probe's systems had to remain operational to collect data on Titan's atmosphere during descent. This information was invaluable for understanding the Moon's complex climate system. Imagine a spacecraft the size of a small car plummeting through an alien atmosphere at supersonic speeds. The engineering prowess required to navigate such extremes is astounding. As Huygens descended deeper into Titan's atmosphere, the heat shield began to ablate to gradually burn away, dissipating the immense heat generated during entry. The probe's descent was a carefully choreographed ballet of engineering and science. Each system, from the heat shield to the onboard sensors, played a critical role in ensuring a successful landing. With each new discovery, our understanding of the cosmos deepens. The challenges faced by Huygens during its descent are a testament to human ingenuity and the relentless pursuit of knowledge. The icy peaks on Titan are composed primarily of water ice. These peaks can reach heights of up to several kilometers, creating a landscape reminiscent of the high mountains on Earth. The composition of these rocks is intriguing because it suggests that the processes shaping Titan's surface might be similar to those found on Earth. This unusual composition is a result of the unique atmospheric conditions on Titan, where methane rains can carve intricate landscapes over time. The Huygens probe used a surface science package to study these winds, measuring their direction and strength as it touched down on the surface. These winds are driven by the sun's heat, which is absorbed differently across Titan's varied terrain. The resulting pressure differences create complex wind patterns. During the northern summer on Titan, winds can reach speeds of up to 2 meters per second, akin to gentle breezes on Earth. In contrast, the southern summer brings weaker winds, typically around 1 meter per second. These seasonal variations are a direct result of Titan's tilt and its long, year-long orbit around Saturn. The surface features of Titan bear the mark of these winds. The dunes and eroded landscapes are testament to the ongoing shaping forces at play. The wind patterns observed by Huygens provide valuable insights into Titan's meteorological processes and the intricate balance of its environment. Unraveling these mysteries allows us to paint a more complete picture of Titan's dynamic surface and its ever-changing landscapes. One of the most striking features captured by Huygens was the network of drainage channels that crisscross Titan's surface. These channels, reminiscent of Earth's river systems, are carved by the flow of liquid methane during heavy rainfall events. These findings offer deeper insight into how Titan's surface has evolved over millions of years. The constant cycle of methane rainfall and erosion has created a landscape that is both alien and yet strangely familiar to Earth-based geologists. By understanding the forces at work on Titan, we can appreciate the beauty of this distant world. Each feature tells a story of the methane cycle that has sculpted its surface over eons. The probe's images also revealed vast plains shaped by wind erosion, similar to the great deserts on Earth. These areas are devoid of the deep channels, but show signs of the relentless action of Titan's winds. The knowledge gained from the Huygens mission continues to guide future explorations, helping us unlock more secrets about this intriguing moon and its unique ecosystem. Titan's surface erosion is a testament to the power of liquid methane and the forces that shape our cosmic neighbors, providing us with new perspectives on the diversity and complexity of worlds beyond Earth. The historic Huygens probe landing on Titan's surface in 2005 unveiled a world of mysteries, including geological features that hint at a past filled with liquid methane. Geologists studying images from the probe have identified dry riverbeds and shorelines that suggest Titan once hosted vast seas of methane. Imagine, if you will, the sight of these long-lost seas. Towering cliffs carved by ancient methane tides would once have greeted explorers, and the echoes of distant methane rainstorms could be heard rolling across the surface. The remnants of these ancient seas can be found in the dry riverbeds and shorelines scattered across Titan's surface. These features are not mere decorations. They are testaments to a rich hydrological past that shaped the world we see today. These geological signatures provide us with invaluable clues about Titan's climatic history and its long-term evolution. By studying these features, scientists can piece together a narrative of how liquid methane has influenced the surface over time. The presence of these dry riverbeds and shorelines on Titan's surface is a reminder that our cosmic neighbors are complex systems with their own histories and transformations. It's an invitation to explore the intricate mechanisms that have shaped this icy moon. Unlike Earth's water, Titan's methane evaporates and precipitates as it cycles through the atmosphere, creating a unique landscape of seasonal variations and dynamic weather patterns. This constant dance between liquid methane and the solid surface has left behind an intricate tapestry of geological features, each one telling a story of Titan's past hydrological activity. By studying these ancient features, we gain a deeper appreciation for the forces that have sculpted and continue to shape this enigmatic world. It is through these remnants of past liquid methane seas that Titan reveals its complex nature and history. The Huygens probe's descent to Titan's surface not only revealed a world shaped by methane, but also offered a glimpse into the dynamic processes that have carved this icy moon over time. This discovery enriches our understanding of Titan's climatic history and its implications for the present-day features we observe today. The evidence of past liquid methane on Titan serves as a testament to the power of natural forces in shaping the worlds around us, and it challenges our perceptions of what is possible beyond Earth's atmosphere. Through these findings, we are offered new perspectives on the diversity and complexity of worlds that lie beyond our own planet, and we are invited to ponder the rich tapestry of processes that have shaped them. The Huygens probe's historic landing on Titan has not only opened a window into this fascinating world, but also serves as a reminder of the unending quest to understand and appreciate the wonders of our universe. At Titan's poles, vast lakes of liquid methane stretch across the landscape. These are not ordinary bodies of water, but part of a complex climate system shaped by extreme cold and seasonal changes. Titan's seasons last approximately 7.5 years, nearly 4 times longer than Earth's. As the sun shines on Titan's north pole, it warms the surface enough for methane to evaporate into the atmosphere, forming clouds that eventually rain down as liquid methane. During winter in the south, Titan's atmosphere freezes out onto the surface, creating layers of frozen methane. When summer returns, these frozen deposits sublimate back into the atmosphere, contributing to the seasonal cycle of methane evaporation and precipitation. Understanding these seasonal variations is crucial for future missions like NASA's Dragonfly, which aims to explore Titan's surface in more detail. The insights from Huygens serve as a foundation for further studies into this enigmatic world. As we continue to unravel these mysteries, we deepen our appreciation for the diverse and complex nature of our solar system's moons. The historic landing of Huygens has opened a window into the wonders of Titan and its polar regions, reminding us of the enduring quest to understand our universe's vast expanse. The organic materials on Titan's surface provide a unique laboratory for studying the origins of life. They offer clues about how prebiotic chemistry might have unfolded in different environments across the cosmos. But beneath Titan's thick atmosphere lies another mystery, one that shapes the moon's surface in dramatic ways: cryovolcanism. The photos revealed a landscape unlike any other in the solar system: vast plains of ice and organic compounds shaped by bizarre geological processes that defy Earth's norms. Among these features are cryovolcanoes, volcanic vents spewing not molten rock, but cold liquid methane and other hydrocarbons. These cryovolcanoes form when the interior heat of Titan melts its icy crust, pushing liquid methane to the surface. This geological activity is called cryovolcanism, a phenomenon unique to worlds with thick atmospheres and icy surfaces. Cryovolcanic eruptions sculpt Titan's surface, creating mountains of ice and depositing dark hydrocarbons that give the landscape its distinctive hue. By unraveling these mysteries, we gain deeper insight into the geological forces that have shaped Titan's alien landscape over billions of years. These readings were crucial for understanding Titan's complex atmosphere, but the turbulence made the task incredibly challenging. Imagine trying to take a precise measurement while being tossed around in a stormy sea. That's essentially what Huygens was doing as it descended through Titan's tumultuous skies. Each image revealed a world unlike any other, where methane plays the role of water, creating rivers, lakes, and even rains of liquid methane. The probe's journey through Titan's atmosphere was a testament to human ingenuity, overcoming immense challenges to unveil the mysteries of this alien world. Titan's dense atmosphere, made primarily of nitrogen with traces of methane, creates conditions where tidal forces can significantly impact the surface and climate. This phenomenon is known as atmospheric tides. These tidal forces can shift the atmospheric pressure by up to 5%, altering weather patterns and affecting surface features such as the dunes in Titan's equatorial region. The data sent back from Huygens showed that these atmospheric tides can also cause variations in wind speed and direction, creating dynamic weather systems that shape Titan's surface. Observations from Huygens revealed methane clouds that seemed to follow these tidal patterns, indicating a complex interaction between the atmosphere and the liquid methane lakes on Titan's surface. The Huygens probe provided a wealth of information that continues to shape our understanding of this fascinating moon. Perhaps one day we'll be able to set foot on Titan ourselves, adding yet another chapter to the story of human exploration. For now, the data and images sent back by Huygens offer a glimpse into this distant world, challenging us to dream of what lies beyond our own planet's atmosphere. But as Huygens began its exploration, it encountered landforms that defied conventional wisdom about ice-rich worlds. Among the peculiar features were icy boulders scattered across Titan's surface. These weren't mere frozen rocks. They were rounded and sculpted by some unknown process. Huygens also detected pancake-shaped domes, which bore an uncanny resemblance to similar formations on Earth. The existence of these features hinted at a complex geological history that scientists were only beginning to grasp. As the probe ventured further, it uncovered signs of tectonic activity. The surface was not static. It was alive with movement and change. These discoveries challenged our existing models of icy worlds, showing that Titan's geological history might be far more dynamic than previously thought. But how did these features come to exist? Huygens provided some clues, hinting at a world shaped by both ice and methane over billions of years. By studying these icy boulders and pancake domes up close, Huygens was piecing together the story of a world far more complex than initially imagined.